before I announce the next speaker, I just sorry. I was told to make an announcement about the posters tonight. The poster session room is now ready for mounting posters, so presenters can go to the events center, which is where we had the reception last night, and mount their posters there. You've got to mount it according to the number that you're assigned, and you're not supposed to mount it anywhere else. If you're in doubt, you can look at the map, which will be mounted at the door, and I have a copy of that. And I'd like to announce the last paper in our session is a paper from France, from Poitiers. And you can note in your book that the presenter will not be Dr. Gros, it will be Dr. Poyu. And the title is Selective Hydrogenation of Fatty Esters in Unsaturated Alcohols and Ruthenium Tin Catalysts.
Good afternoon. Sorry for my pronunciation, but it's difficult to speak English. The study that I'm presenting today has been carried out in the laboratory of catalysis in organic chemistry at the School of Engineering of the University of Poitiers, whose director is Professor Barrault. Generally speaking, our work consists on valorizing natural feedstocks issued from agriculture or fisheries. In particular, we have studied the hydrogenation of methyl oleate into fatty alcohol. These programs has been funded by both French and European extensive programs. These programs are focused on the valorization of basic raw materials such as sugar, protein, cellulose, or oils issued from agriculture and fisheries for non-food industries. Natural feedstock presents several advantages: the diversity of the available natural products, the renewable character of raw materials, and the development of processes due to agro-research favoring the qualities and quantities of these compounds. Moreover, in chemical industry, the use of natural feedstocks opens a new scope of investigation of new processes and new products, some of which being quite different from those accessible by petrochemical paths. In fact, the global production of oleochemical compounds increases from about 30 million tons per year in 1960 to 80 million tons per year in 1990. The expectation for the 21st century is around 1 million tons. Of about 80 million tons of annual oil productions, only 30% is used for industrial application or agrochemical developments. The remainder is used for animal or human foodstuff. Therefore, natural oils represent an important source of raw material at low prices for manufacturing, in particular, intermediate or end products such as cleaning agents, detergents, inks, food emulsifiers, pharmaceuticals, or cosmetics. Now, I would like to speak about the chemical composition of fatty compounds issued from soybean, palm, colza, or sunflower. The main chemical component of these oils is the triester glycerol. The hydrogen chain and the unsaturation depends on the plants. In the case of the sunflower oils, the main hydrocarbon chain contains 80 carbon atoms, and we can have 1, 2, or 3 unsaturations. The hydrolysis or triglycerides can release fatty acids and glycerol as a side product. the fatty acid can be used for different transformation, esterification, amination, oxidation, or hydrogenation. In our work, we have studied the selective hydrogenation of methyl oleate issued from sunflower oils into oleyl alcohol. Yet, this reaction scheme shows that two primary compounds, oleyl alcohol and methyl stearate, can be obtained, and the competitive hydrogenation of these two compounds can occur and form a saturated alcohol, stearyl alcohol. From this scheme, it can be seen that the chemioselectivity of the reaction must be controlled by varying the adsorptions of unsaturated carbonyl compounds to selectively adsorb the carbonyl group instead of the olefinic bond. Thermodynamically, the hydrogenation of a CC double bond is easier than the hydrogenation of a CO bond. The main industrial processes use different types of catalysts. Copper bromide or zinc bromide can be used for manufacturing saturated or unsaturated alcohols. The low activity of this catalyst, however, requires severe reaction conditions, high temperatures, and high pressures. Well, the aim of this work is first of all to find new type of catalysts, so as to be able to carry out the reaction in the mild conditions. And secondly, to replace the toxic premium due to the latest rules and regulations concerning the environment. Recent studies show that transition metal, and in particular noble metal, associated with a promoter like tin, are selective in the reduction of ester to saturated alcohol. These catalysts are not selective to unsaturated alcohol. On the other hand, according to Narasimhan, a ruthenium tin boron catalyst supported on alumina is selective to unsaturated alcohol for a conversion of 80%. It is well known that bimetallic systems present several advantages, namely transition metal effect by activation hydrogen and the promoter effect. A geometric influence by dilution of the metal size. The consequence is the decrease of a CC double bond adsorption on the surface of a catalyst. B, an electronic effect. Tin is added to the noble metal to enhance the adsorption and the hydrogenation of the carbonyl bonds. This increase is could be due to the decrease of electronic properties of the metal size. Now, I speak about experimentation. The hydrogenation was carried out in the stainless steel batch reactor. Hydrogen pressure 80 bar, temperature 270 degrees. The amount of methyl ester is 100 milliliters with no solvent. Molar ratio hydrogen ester 1.5 and the catalyst weight 2.2 grams. The ester condition and the product distribution was determined by two GPC analytical systems equipped with FID. In the first part of our works, the hydrogenation of, the catalysts were prepared by different techniques, starting from ruthenium chloride and tin chloride, and a specific preparation with a reduction state involving sodium borhydride, as reported by Narasimhan, an impregnation of a super for 12 hours, and a reduction with sodium borhydride. Now, in the first part of our works, we have studied the hydrogenation of methyl oleate over monometallic catalyst. This table shows that nickel, ruthenium, or palladium catalysts are both active and selective to the formation of saturated ester. We can notice that ruthenium catalyst favors the hydrogenalysis of ester because the selectivity to hydrocarbon and acid is around 30%. These catalysts are not selective to alcohols. Here, activities and selectivities of ruthenium tin boron catalysts with different amount of tin are reported. First, we can notice that the addition of tin decreases the activity of the catalyst. Therefore, we can notice that the oleyl alcohol or unsaturated alcohol was formed, and it is clear that the selectivity to unsaturated alcohol increased when the tin-ruthenium ratio varies between 0 to 4. Excuse me. Yet, we have never obtained a selectivity to unsaturated alcohol of 80% for a combination of 80% as reported by Narasimhan and colleagues. Indeed, this figure shows that the selectivity of two unsaturated alcohol was decreased by a secondary reactions. It is not clearly shown by Narasimhan groups in previous works. In fact, we have only obtained 30% of oleyl alcohol over ruthenium tin catalyst with a 4 tin-ruthenium ratio. In fact, these authors do not mention the formation of heavy esters we have determined by GPC-SM analysis, and this heavy ester issued from the transesterification between methyl oleate and alcohol form. We can notice at the beginning of a reaction the transesterification state is more rapid than the hydrogenation state. We can notice, therefore, that the selectivity to heavy ester is more than 75% after 1 hour reactions. On the other hand, we can notice that the hydrogenation of heavy ester or oleyl oleate gives 2 moles of unsaturated alcohols or oleyl alcohol. In order to obtain further information concerning centers of catalysts involved in the transesterification, we have studied the reaction between methyl oleate and stearyl alcohol in the presence of alumine or tin oxide on alumine. The reaction was carried out at 270 degrees in the same batch reactor without hydrogen. The results presented here show that the tin species are a significant effect in the transesterification. We can think, therefore, that the active center is a tin species. In order to improve and to understand the selectivity changes, we have studied the influence of the preparation method of a catalyst. This figure shows the change of methyl oleate conversion with reaction time. First, we can notice that the activity of catalyst depends on its preparation. Indeed, the catalyst prepared obtained from solvent techniques or from a drag impregnation of a support presents an induction period of about 2 hours. On the other hand, the catalyst prepared by the Narasimhan method with a reduction with sodium boride is more active without this induction period. Apparently, the reduction step with sodium boride improves the reducibility of ruthenium tin systems. From these results, the questions arise concerning the boron effect on the catalyst or on the reaction. Here, the selectivity to different catalyses to unsaturated alcohol are compared. It is obvious that the catalyst reduced or not reduced with sodium boride have the same selectivity to unsaturated alcohol. We can think, therefore, that boron had no effect on the reaction. It is particularly demonstrated with the sol-gel catalyst, which, without boron, is an efficient catalyst in the hydrogenation of methyl oleate to oleyl alcohol. On the other hand, we can notice that the sol-gel catalyst gives less heavy ester than the other solids. In order to show the effect of the reduction step, we have characterized the different catalysts on TPR, temperature program reduction. This figure shows the change of TPR curves as a function of the amount of reductor introduced. Solids activated with sodium boride are more easily reduced with hydrogen. Indeed, the maximum reduction temperature decreases when the amount of reductor increases. On the other hand, the TPR peak of ruthenium catalyst reduced with sodium boride is sharper than the other solids. This could be indicate a great homogeneity of the catalyst and a decrease of average particle size of ruthenium. In the same way, the TPR curves of ruthenium tin show that there are the strong interactions between tin and ruthenium. Tin decreases the reducibility of ruthenium. It has been suggested that tin species covered the ruthenium particles and inhibits the hydrogen adsorptions or limits on its hydrogenating properties. These results were confirmed by hydrogen and carbon monoxide chemosorptions. In the presence of tin, the hydrogen adsorptions is suppressive, while carbon monoxide chemosorptions is also strongly decreased. In fact, the accessibility and the electronic properties is more modified by tin species. The XPS characterization gives some different information concerning symptoms on the surface of a catalyst. Over ruthenium monometallic catalyst, there are only ruthenium oxide on the surface of a catalyst. Whereas over ruthenium tin boron, ruthenium metallic particles can be observed with tin oxide and different boron oxides. Finally, in these works, we have shown that hydrogenation of methyl oleate into oleyl alcohol was performed in the presence of ruthenium tin on alumina. Indeed, the monometallic catalysts are not selective to unsaturated alcohol, whereas the addition of tin increases the selectivity to this unsaturated alcohol. Tin species, however, favors the side reaction between methyl oleate and alcohol formed. In fact, the selectivity to unsaturated alcohol is lower than the one proposed in the previous works due to the trans-esterification. This trans-esterification is modified by tin species. On the other hand, selectivity and activity of catalysts were greatly influenced by method preparations. The reduction step with sodium peroxide improved the dispersion and the homogeneity of ruthenium particles, and the reduction stabilized the ruthenium metallic particles on the surface of a catalyst. Nevertheless, a catalyst prepared by a salt gel techniques gives a good yield to oleyl alcohol. It seems that boron have no effect on the reaction. In conclusion, we can propose that the active center into hydrogenation of methyl oleate to oleyl alcohol is constituted by ruthenium metallic particles in active reaction with tin species. Thank you for your attention.
Questions? I was wondering if you looked at any other substrates where you want to preserve the olefin function while you're reducing the ester. Have you looked at any substrates where those two functions are closer together? Because you've got a long chain in between them, and that I was just wondering if you've looked at what happens when those two functionalities are closer. No. Any other questions?
Do you see any migration of the double bond in any of the products, that is in the oleyl alcohol? Is there any isomerization of the double bond, or even the other products that you get, the ester, for example? No double bond migration?
No.
Okay.
Any other questions? Well, if not, then let's thank the speaker and all the speakers. That concludes the session on selective hydrogenation. I just wanted to mention two things to you as you're leaving. Again, Dr. Blaser has brochures for the Fine Chemicals meeting in the fall of '96 in Zurich, if you're interested. And also there were some brochures also for a workshop, a pre-Congress workshop that we're organizing on heterogeneous catalysis and organic reactions. And if there aren't any more back there, I have more of those that you can get.